Okay, welcome back. So this is week 6 of the discussion hours. We will actually, uh, so I'll start by actually giving some clarifications to the previous problem that we solved, which was, so I'll give a quick recap of what we actually did. So we were actually trying to evaluate the flow field that is being generated inside a square duct, where the flow is actuated by applying a constant pressure gradient and the crux of the problem involves the fact that now since this is a duct, so now the velocity profile will no longer be just a function of one variable, which was the earlier cases which we learned it in plane possible flow, but now it will be a function of two independent variable, which is x and y, because we have the geometry which is having a finite length or a finite width and a finite height, although the length of the pipe was infinitely long in the z direction. Okay, so this is something that we had, and we were asked to calculate for the flow field, for which we wrote the Navier-Stokes equation, let's say in the z direction, and then we saw that. So basically, we also tried to incorporate the non-dimensional approach here, where we chose various characteristic scales for the Partinan variables, and then evaluated the corresponding non-dimensional numbers, and then substituted or converted the dimensional equation into the non-dimensional equation, uh, which we eventually got it as a Laplacian equation with a constant term. So we called this as a Poisson equation, because of the fact that because of the fact that this equation is no longer homogeneous in W. Okay, and then we said that the solution is going to be a superposition of uh, two variables, which is W1 and W2. Typically, because the idea is to convert the Poisson equation into a homogeneous equation, which is the Laplace equation. So what we did is we dumped this constant of -1 into the parameter, or I should say the variable, W1, and then eventually, solve for the ODE that governs W1, because W1 we took it to be just a function of X. But remember that we can also take W1 to be function of Y as well. Okay, then we will see very shortly that the separation constant, the way you take the separation constant, in fact its sign would basically change if you choose W1 to be a function of Y instead of it being a function of X. But the essential physics of the problem will not be changed at all, because it's a duct basically. So either way the problem is symmetric about the X and the Y axis, precisely. Okay, so it doesn't matter actually if you take the separate. If you take the variable W1 as a function of Y as well. Okay, but so what we did is we just solved for W1, which was an ODE, and as I said, the idea is to basically dump this non-homogeneous part into W1, and then find out an equation which governs W2. So we saw that W2 is basically governed by the Laplace equation, which was something like this. And then we wrote the boundary condition in terms of W2. And then we stopped that by looking at what would be the separation constant in this scenario. And we actually ran into some confusion here of choosing into the separation constant, which I will try to clarify in this discussion hour. So before actually trying to see what the separation constant, we know that its magnitude is going to be lambda square, but it's actually the sign of the separation constant that becomes important in this scenario. Okay, so for that, what we'll do is we'll kind of rewrite the boundary condition in a different way. So we'll try to write the boundary conditions in a different manner, as I was saying. So what we had earlier is just we had this x direction, let's say in this way, and we have this y direction along the height basically, where we saw that this x varied from x equal to -1 to x equal to 1, which means that this is x equals to 0. And we also said that our y also varied from y equal to -1 to y equal to 1. Okay, which means that this is basically equal to y equal to 0. Okay, so we had our axis that is being centered at x0 y0. That's how we have actually taken the axis of this problem. Okay, and since the variables are just non-dimensional, so we are only interested in non-dimensional quantities. So what we said is that we said that our one of the boundary conditions was that u. In fact, let's see the boundary conditions once again. Okay, so we said that u at x equal to 1, which is basically on this face. We said that sorry. So we said that, so the physical boundary condition was that we had no slip boundary condition on the four walls, okay, which means that the velocity at the four walls of the duct is just going to be equal to 0. So that's how we oops, sorry. So that's how we wrote the boundary conditions. So then let's just write it once again. So we said that u at x equal to 1 for all y, which means this surface that I am writing. This is equals to 0 because of the no slip boundary condition. And then I can write this boundary condition because I know that u is equal to u1 of x plus u2 of xy. So I can write this at u at x equal to 1. In fact, this is u1 at x equal to 1, but u1 is just the function of x. That's how we have taken u1. So this is just going to be this plus u2 at 1 comma y is equal to 0. Okay. And so now what we said is that since this is a function of y, this is a function of y, okay, and this is just a function of x, okay, which means that the only possibility for these two terms going to 0 is the case that my u2 at 1 comma y has to be equal to 0. Okay, that's uh, that's one way of uh, saying this boundary condition. Okay, that's one boundary condition that I would right here. Okay, the second boundary condition is that, so what I was writing is that I say that u at x equal to -1 at y, this is 0, and this is true. Okay, this is not, it's not that this boundary condition is wrong, this is true, but so in solving this problem analytically, it becomes easier to actually write a different boundary condition, which is kind of a, it's kind of a rephrase or a reformed version of this boundary condition. And this comes from the fact that, see, I know that my velocity here and my velocity here is equal to 0 basically, which means that the velocity profile along x has to be symmetric. So another way of saying this, I can equivalently write that from this boundary condition is my del u del x at x equal to 0 for all y is equal to 0. And this is an equivalent statement of saying that my u at x equal to 1 for all y is 0 basically. And this is and this argument is basically of the fact that my profile is going to be symmetric because the velocities are same at x equal to 1 and x equal to -1. My profile then has to be symmetric at the midplane. That's what I'm trying to say. Okay, which means so this is the symmetry argument that that we can infer, and then I can then write this boundary condition as del u1 by del x. But I know that my del u1 by del x will simply be equal to du1 by dx because of the fact that u1 is just a function of x at x equal to 0 plus del u2 by del x evaluated at x equal to 0 comma y. This is equal to 0. And then I know that since this function, again the same argument, that since this function is a function of y and this is just a constant in fact, which just means that my del u2 by del x at x equal to 0 comma y is equal to 0. Okay, this is the second boundary condition, which is, again I repeat, this is one way of writing this boundary condition as as invoking the symmetry argument into the picture. Is this boundary condition that I have written. Okay, so you can say this is kind of a reformed or a or rephrased, or maybe I should call it the reformed function of boundary condition of this scenario. Okay, again physically it just means that at x equal to 1 and at x equal to -1 the profile is going to be symmetric, therefore its derivative with respect to x at x equal to 0 has to be 0 basically. That's one argument. Okay, and it's called as the symmetry argument. Okay, so I'll name this as my second boundary condition. Okay, and then let's try to see the boundary conditions in y as well. So I will, so as I know, I said that u for all x at y equal to 1, which is basically on this, I know that u is 0. Okay, and I can write this as u1 of x plus u2 of x comma 1 is equal to 0. So one of the conditions then becomes is u2 at x equal to 1 is equal to minus of u1 and x equal to 1, and I know what's the value of u1, right? So I know that my u1 is what? So my u1 is okay, I wrote this in terms of w, so maybe I should write I'm sorry for that. I wrote the velocities in terms of W actually. Uh, okay, so this is W. Please correct this. It's just the notation. So I wrote these velocities as W. So these things will be W. Okay, this is W, and yeah, so please correct this. These things are going to be W. I'm sorry for messing with the notation. Quite a lot of changes. This is W. This is W. And then this is also W, which means that these are all going to be W. Okay, and then I said that my W1, which I have evaluated before, it's already evaluated, right? My W1 is going to be equal to x, half of 1 minus x squared. So this is going to be equal to half of 1 minus x squared. That's W2. And then this happens to be my, let's say, third boundary condition on the top face, basically. Okay, so this is on the top face. Okay, similarly, I can say that I know that my W that's on the bottom face, that x at y at equal to -1 is equal to 0, and this I can equivalently then write at del W by del y, sorry, at y equal to 0 for all x equals to 0. This is again the symmetry argument that I was using in the previous case as well. So this just comes from the symmetry, and it's all because of the fact that at the top and at the bottom face my velocities are just equal, and on account of symmetry, then I can tell that the derivative with respect to y at the center is just going to be equal to 0. Okay, so that's the symmetry argument. Okay, and then I can write W as what? Maybe del W1 by del y plus del W1 by del x evaluated at, sorry, this is y. This is del W2 by del y evaluated at 0 comma x, and then this is equal to 0. Okay, and then I can tell that, see, this term is anyway 0 because u1 is just a function of x. So which means uh, I can tell that del w2 by del y evaluated at 0 comma x is equal to 0. Okay, this becomes my fourth boundary condition. So if you carefully now have a look at the boundary condition, essentially what we have done is we actually wrote boundary conditions, you know, for what? For this plate and at the center, basically. Okay, which means it is we can actually now, so it just suffices to now actually solve the problem in this in this in this hatched area only, because whatever the solution that we'll get in this hatched area, which means that my x now varies from 0 to 1 and my y now varies from 0 to 1, whatever the solution that we'll get in this hatched area is going to be the same in all the rest of the, you know, of the four or of the three quadrants, typically because the problem is just symmetric. Basically, that's one way of putting it. Okay, so then so then what you need to do is, okay, so now you know that. So now from the boundary condition, so let's write the boundary condition once again. So okay, so the consolidated boundary condition, I should say. So maybe the first one is w2 at 1 comma y is 0, and del w2 at del w2 by del x, okay, at 0 comma y, okay, is 0. This is the conditions on x, and then I have w2 at x comma 1 is basically equal to minus of half of 1 minus x squared, and del w2 by del y at x at all y, all so basically at all y's is, which is 0, and for all x this is equal to 0. Okay, these are the two boundary conditions. So you see now that along x, so this is the boundary condition along x, and this is the boundary condition along along y. And now you can see that you just have x and y varying from 0 to 1, right? As I said, it just suffices to only solve the problem now, because the problem is just going to be symmetric in all the four quadrants, okay? But more importantly, what you see that along x, the boundary condition is homogeneous, okay? So when x varied from 0 to 1, so when my x, varied from 0 to 1, if I go along, so basically if I go along or if I march along this direction, I know that my boundary conditions are homogeneous, okay? My boundary conditions are homogeneous, okay? Fine, which then means that whatever the solution that I'm going to get along x, that is capital X of x is the variable along x, okay, it should have homogeneous boundary conditions, and that implies that the separation constant that we have chosen over here, which is this has to be equal to minus lambda square, because I want my solutions to be periodic along x direction, because I have homogeneous boundary condition at x equal to 0 and at x equal to 1, okay? Then it suffices, or then the only possible way of lambdas of this sign that it can be is negative, because I know that then only, if I solve this, if I basically solve this, or if I equate this and solve for x, I know that I am going to get periodic solution, okay? So I'll write it down that from the boundary conditions, okay, since along x we have homogeneous boundary conditions, so we seek periodic solutions along x. Hence, the separation constant, which is minus lambda square, the sign of it is negative basically. Hence, the separation constant is negative. Okay. So now you can indeed prove that you are going to get periodic solution if you just solve now for x of x. So for x of x, so x of x satisfies what? It is x double prime by x equal to minus of lambda squared, which means you can write it as x double prime of x plus lambda square x of x, and this is equal to 0, which means then my x of x satisfies a cos lambda x plus b sine lambda x. Okay, why? That is simply because you substitute the form that x of x is equal to some e power mx into this equation. You will see that your values of m is going to be plus minus of I lambda, and if you then write e power I lambda as, using the fact that cos I theta is equal to e power I theta is equal to cos I theta plus I sine n theta, you are simply, going to get this solution. That's how you actually solve second order, constant coefficients ODEs basically, okay? Substitute the form that x of x is equal to e power mx into this, okay? I believe you have done this many a times, so you are clear on this, okay? And indeed, you can see that the solutions along x are periodic, where, where now we need to find these constants a and b by invoking the boundary conditions, okay? So, so let's have a look. So what do we have? So first, I know that at x equal to 0, I have the fact that del u2 by del x evaluated at x equal to 0 for all y is 0, okay, which means I can then write, so just we need to do the derivative, so this becomes minus a lambda sine lambda x plus b lambda cos lambda x, and then you need to use the fact that x is equal to 0 and this is 0, which means that this term would just go to 0 and you just have, b lambda cos lambda x as 0. Uh, Hold on. It- Okay, did I do any mistake? So if I substitute x to be 0, then this is 0. Okay, sorry. Yeah. So, so what I do is I substitute x to be equal to 0. So then, okay, let's substitute. So it is a lambda sine of lambda 0 plus b lambda cos of lambda 0 is equal to 0. So this term will anyway go out to be 0, while cos lambda 0 is going to be is just cos 0. So this is going to be equal to 1, which means that for this to be equal to 0, I should have b to be equal to 0. Okay, so that's the condition that you get when you use the fact that this del u2 by del x evaluated at x equal to 0 is basically 0. Okay, which means that my x then becomes a cos lambda x, and then I use the other condition, which is the fact that x. So what's the other condition? So the other condition is that my u2 at x equal to 1 for all y, this is equal to 0, and I know that u2 is equal to x of x times y of y is equal to 0, but I know that now x is equal to 1, so this means x at x equal to 1 times y of y, this is 0. Okay, but from this I can only conclude that my x at x equal to 1 is 0, and this is because of the fact that y of y can't be equal to 0. Okay, because if y of y is 0, then what will happen is my u2, which is defined, so if y at all y becomes 0, what will actually happen is my u2, which is a product of x and y, this will turn out to be 0, which means it's a trivial solution. Okay, but we are not looking for trivial solution, which means that the only possible solution is that x at 1 has to be equal to 0. Okay, that's because since y of y can't be equal to 0, else we shall encounter trivial solution, which means that my x of 1 has to be equal to 0. So let's evaluate x of 1. So x of 1 is a cos lambda is equal to 0, which means a can't be equal to 0 because we know that b is already 0. So if a happens to be 0, then you know x will turn out to be 0, and again we'll get the trivial solution. Okay, which means that the only possible solution is cos lambda equal to 0, or then my lambda is going to is basically going to be equal to twice n plus 1 pi by 2, where n varies from 1 to up to infinity. Okay, now we know that since this lambdas or this lambda specifically depends on the value of n, and I know that this n are going to vary from 0 to 1, 0, 1 to up to infinity. This just means that for a generic n, I can write my eigenvalue. So this lambda happens to be my eigenvalue as twice n plus 1 pi by 2 for a generic n. Okay, and this lambda, this is actually known as the eigenvalue. See, this is actually called eigenvalue because you know that the condition is satisfied only for some specific form of lambda, which so it's not that any lambda will satisfy the solution, but lambdas of the form twice n plus 1 pi by 2 will satisfy this solution, and that's actually how the the reference of eigenvalue comes here, because you know that the solution is not always satisfied, but it is satisfied for any value of n provided lambda has this form, which is twice n plus 1 pi by 2. Okay, and that's typically is the hallmark of a eigenvalue problem, and these lambdas are known as eigenvalue, and this xn's andyn's that you are going to calculate, they are actually known as eigenvectors. Okay, so then for any generic n, I can write my xn as some an cos lambda nx, and I know that lambda n is equal to twice n plus 1 pi by 2, so I can write my xn as an cos twice n plus 1 pi x by 2. Okay, so that's it, that's your xn's precisely. So then we are now left to calculate the yn. See, an is yet to be determined, and we will see how we will determine this an, but before that let's evaluate the yns. Okay, or I should say y of y first, and eventually we'll see that they can also be written for a generic n. Okay, now let's see what y satisfied. So we had is this equation, where it is, so it's here that minus y double prime by So this minus y double prime by y, this is equal to minus of lambda square. So typically it becomes, so if you use that, it just becomes y double prime by y minus lambda square is equal to 0, which means that y double prime minus lambda square y, and this is equal to 0. And that means that y as a function of y is going to be equal to some cn times exponent of minus lambda y, okay, plus some dn times exponent of lambda y, okay. Again, because of the fact that so it's the same thing that you need to do. You need to take y to be equal to y of y to be equal to some e power my, okay, and then you need to substitute it. If you substitute, you'll basically get the fact that m square minus lambda square equal to 0, which means that m is going to be equal to plus and minus of lambda, and you know that the solution is basically this. So one solution is going to be equal to e power lambda y, and the second solution is going to be equal to e power minus lambda y, and basically these two solutions are linearly independent, so the entire solution is going to be equal to the linear combination of the two solutions. That's what exactly we have written here, okay. So one small trick now, what we'll do is we'll write down this exponential term as follows. So what we'll do is we'll write this cn's as cos hyperbolic, maybe, yeah, so you can write it as some cos hyperbolic lambda and y plus sine hyperbolic lambda and y, okay, because you can write the fact that uh, your cos hyperbolic lambda and y can be written as e power lambda and y plus e power minus lambda and y, okay, by 2, and sine hyperbolic lambda and y, you can write this as e power lambda and y minus e power minus lambda and y, okay, by 2. So then if you just add these two, you're just going to get the same thing, okay. So a better way of representing it, representing this in the form of cos hyperbolic is in the form of sine hyperbolic functions, cos and sine hyperbolic functions, and we will see why it's a better way of representing exponent of minus something and exponent of plus something as a cos hyperbolic and a sine hyperbolic thing, okay. So then my y of y is equal to some cn times cos hyperbolic lambda n y, which we already know, and this is equal to some dn. There's a dn here, so this is dn. Sorry. Okay, so there's a dn times sine hyperbolic lambda n y. Okay, so that's it. We know xn, and this is true for any generic n. Okay, so that's it. We know xn, we know yn, and so my u2 as a function of x and y is then going to be the superposition of all the xn's and yns, because of the fact that your governing equation is linear. So this is going to be equal to sum over n equal to 0 to infinity xn of x times yn of x. For that is because your u2 is going to be equal to x0 y0 plus x1 y1 plus x2 y2 and all these things. So for a generic n, it's just summation of all the modes typically. That's so any value of n, we call it as modes in eigenvalue analysis, and your entire solution is the superposition of typically all the modes. That's one way of saying this, okay. So let's then write it. So it's summation n equal to 0 to infinity xn. So what is xn? Xn is equal to an cos twice n plus 1 pi x by 2. So it is an cos twice n plus 1 pi x by 2, and yns are going to be equal to cn times cos hyperbolic, lambda and y, where lambda and we already know. Just for the sake of keeping it small, I'm just writing this in terms of lambda n only, and then this is equal to plus dn times sine hyperbolic of lambda and y. And what now we'll do is see these ans and these cn's can be multiplied, because these are just some generic constant. So what I'll say is that an times cn is just equal to some other constant, which I will call it as cn only, okay? Because this is just a generic constant. That's the idea. And similarly, an times dn, I will just call it as dn itself. You can call it as anything, some en or fn, because they are just generic. So instead of just using in another constant, I'll just call it as cn and dn respectively, okay? Because these are some arbitrary constants. So then I can write this as sum over n equal to 0 to infinity cos of twice n plus 1 time pi x by 2, okay, and then this is cos hyperbolic of lambda and y. Sorry, there is going to be cn as well. Okay, so this is going to be cn times cos hyperbolic of lambda and y plus dn times sine hyperbolic of lambda and y. Okay. All right, that's it. So this is going to be your u2 as a function of x and y. Okay. So now what we are left is we are just left to evaluate these cn's and dn, and for that we have two boundary conditions if we move along the y direction. For example, I know that at y equal to 0, my del u2 by del y, this is 0. Okay. And from here, what can I say? Okay, so let's do this. So then if I invoke this into this expression, I can tell that summation of n equal to 0 to infinity cos of twice n plus 1 time pi x by 2. Okay, see. Okay, let's do it. Let's do it and then we'll see. So this is Cn times lambda n. The derivative of cos hyperbolic is going to give you sine hyperbolic lambda and y. But I need to evaluate this as y equal to 0. Okay. Plus the derivative of sine hyperbolic is going to give you cos hyperbolic. So this is dn lambda cos hyperbolic lambda and y evaluated at y equal to 0. And this is 0. Now we know that sine hyperbolic 0 is 0, which means that this term is just going to be equal to 0. And from this condition, you can then say that sum over n equal to 0 to infinity cos of twice n plus 1 times pi x by 2, okay, times dn lambda cos hyperbolic 1 is just 1, which means that this is just going to be equal to 0. Okay. So the only possibility for this to be 0 is that your dn's has to be equal to 0. Okay. Or else this is not going to be equal to true. Okay. Because you know that yeah, so for any n, for any n, for this to be equal to true, you just have one possibility that your dn has to be equal to 0. That's the only solution that we have. Okay. And from the second condition, what you can do is you can find the other one, which is cn. So what we'll do is, like, at y to be equal to 1, okay, I know that my u2 at x comma y equal to 1 is equal to minus of u1, which was equal to minus of half of what, it was x square minus 1, I guess. Let's see, what was that? Oh, sorry, it is 1 minus x square, which I will write it as, so I'll just not write the minus sign, and I'll write it as half of x square minus 1. Okay. All right. Then I know that dn's are 0, which means that this is just going to be equal to sum over n equal to 0 to infinity cos twice n plus 1 by 2 pi x. I know that dn's are already 0, so I'll not bother about these dn's. And this is cn times cos hyperbolic lambda, that's it. Okay. Because I'm evaluating this as y equal to 1, so this becomes cn cos hyperbolic lambda, okay, because y is 1, this is just lambda n, and then this is equal to half of x square minus 1. Okay, so I'll write this. So this is an important concept. So first of all, I'll write this as sum over n equal to 0 to infinity. Okay, so whatever the functions that are not dependent on x, I will just write it first. So it is cn by 2 times cos hyperbolic lambda n times cos twice n plus 1 by 2 times pi x, and this is equal to half of x square minus 1. Okay, so if you little bit pay a closer attention to the above series, so what is this? This is just a series, right? It's a series in n, and I'm telling that a series in n is equal to a function. And if you basically pay a closer look, this series is nothing but it's a Fourier. So this is a Fourier cosine series where your x basically varies from 0 to 1. Okay, that's exactly what you have if you look at these series. Okay, so then these cn's, these are nothing but it's the Fourier cosine coefficients of this Fourier cosine series basically. But there is a concept. We know that the cosine series, you can, so when x basically goes from 0 to 1, you can equivalently write a cosine series as well as a sine series. In this case, it happens that, it becomes a cosine series. But remember that when, we are in midway in the orthogonality, so there is basically known as then orthogonality interval of these cosines and sine functions. So these cosines and sines, they are known as orthogonal functions in the interval minus pi to pi, basically. Okay. So the point is, for any function in the half interval, you can also write a Fourier sine series, you can also write a Fourier cosine series. Here it so happens that this series becomes a Fourier cosine series, but sometimes you can encounter a fact that you can see that you have a function and you can also have a Fourier sine series, and accordingly you then need to calculate the Fourier sine coefficients for that particular Fourier sine series. Okay, so that's the idea, because midway between the half interval, you can have a Fourier sine series, you can have a Fourier cosine series as well for any functions, basically. Okay, so there is something known as an odd extension and even extension. So you can so since you know the function in just the midway from x equal to 0 to x equal to 1, you can make the function behave as an odd function, or you can make the function behave as an even function, accordingly how you want. Okay, and that's so in this way. Okay, in this way, so for example, if I, so this is so half of x square minus 1. Okay, this is an even function, right? Because if I put x equal to minus 1, I'll just get this function, just f of minus x is just equal to f of x. Okay, but it can so happen then this function may, let's say this function is x cubed. Then you will say that, okay, how can I write a odd function in a Fourier cosine series? You can do that because you only know the function in the mid interval from x equal to 0 and 1. Okay, so what happens at minus 1 to 1 is still at between minus 1 to 0 is still unknown to you. Okay, so then what you say is, okay, I can make the function behave as a behave as an even function in the interval minus 1 to 1, such that in the entire interval from minus 1 to 1, the function is kind of an even function, basically. Okay, so what I was actually trying to say is, uh, okay, because I know the function, from x equal to 0 to x equal to 1, let's say the function is something like this. Okay, I can either, make the function behave as something like this, which becomes an odd function then. Okay, or I can make the function behave as something like this. Okay, which becomes an even function, because you know that f of x is equal to f of minus x here. Okay, so I actually don't care what the function behaves in the interval that is outside my domain, and I don't actually have that in my disposal, right? So what I can then do is I can then make the function behave like an even function or an odd function, whichever way is suitable for writing, whichever way is suitable for writing the Fourier series. Okay, that's the concept that you need to use while you are, trying to figure out what these constants actually will be. See, luckily in this case you have an even function, so it sounds well. But it can so happen that there can be situations where, x varies from 0 to 1 and you end up getting an odd function. Okay, then you should not, panic, because the definition of Fourier series then says that, okay, Fourier cosine series are written for even function, but remember that's only the half interval that you are writing. So in the other half, you can make the function behave like an even function such that you can then write a Fourier cosine series. Okay, that's the idea. Okay, these are the small nuances that basically comes from the knowledge of Fourier series. Okay, but anyways, so what we now require is, we now require to, evaluate the function Cn. So what I will do is, so there is something now known as an orthogonality principle. Okay, there is something known as an orthogonality principle. So the orthogonality principle says uh, that for, orthogonal functions, for instance, so I hope you realize that these functions like 1 sine x, cos x, sine 2x, cos 2x, dot dot dot, up to sine nx, cos nx, these are actually known as orthogonal functions in the interval minus pi to pi, where x basically goes from minus pi to pi. But here we know we have x from minus 1 to 1, but that doesn't matter because we can always do a change of variable. Okay, so then what you can do is, we can use the orthogonality principle, and I will not go into the details of that. You can have any, so for instance, I'll just write one orthogonality principle. For example, integral minus pi to pi sine mx sine nx. So this integral is going to give you 0 when m is not equal to n, and this integral is going to give you pi when n becomes equal to n. For example, there is one more orthogonality, which is minus pi to pi sine mx cos nx. This integral is always 0 for all values of m and n. Okay, and there is one more. Okay, I'll write it down. So the last orthogonality relation is integral cos mx cos nx dx. So this integral is going to give you 0 for m not equal to n. This integral is going to give you pi for m equal to n not equal to 0, and this integral is going to give you twice pi for m equal to n equal to 0. Okay, you can do the integration and check these results for yourself. So these results that I have written, these are known as the orthogonality relations of cosine and sines. So what we'll do is we'll just apply orthogonality relations in this equation. So then what should I do? So what I'll do is I'll multiply. So if let's say I call this as some you know what to say, some m, I'll multiply this by cos nx and then integrate it from 0 to, so in this case I'll integrate it from 0 to 1. Okay, because I only have the half interval here, but you can also integrate from -1 to 1, and you will see that this is 2 times the integral from 0 to 1 because the integrand is an even function. You can basically figure it out. So I'll not do the math here because this is not actually the scope for this course, but I hope the background that I have said that will help you to understand what actually is happening in when we use the orthogonality principle. Okay, so then I'll skip the intermediate algebra, and I'll just write what Cn would be. So what you need to do is you just need to, so as I said, you just need to multiply this by a cos mx and then integrate it from -1 to 1. That's all that you require to do. Okay. So the intermediate steps, as I'll say, I will skip. So then your Cn's, so this Cn will basically be equal to okay. So I'll just write it down. So this Cn's will be equal to what? Cos hyperbolic. Okay. So this is going to be equal to 2 by cos hyperbolic lambda n. Yeah, so it's 2 by cos hyperbolic lambda n times, there is going to be a half here. Okay, sorry. No, this is not going to be a half. So there is going to be a 2 here. Okay, times integral 0 to 1. Okay, half of x square minus 1 times cos of twice n plus 1 by 2 pi x dx. Okay, so if you do some algebra, okay, that's the final, remember that's the final answer that I'm writing, but what you can do is just invoke this orthogonal. So basically you need to invoke this orthogonality relation into this integral. That's all that you require to do. Okay, so then your Cn's are going to be equal to what? So your Cn's are going to be equal to 2 by cos lambda n times integral 0 to 1, okay, x squared minus 1 times cos of twice n plus 1 by 2 times pi x dx basically. Okay, that's it. That's your Cn. So you can so you can easily do this integral. It's just, so all you need to do is apply. So you'll have x square times cosine of this function minus cosine of this function. For this you need to apply integration by parts. Okay, and integration cosine is just going to give you sine function. Okay, so that's it. That's your Cn, and so your entire solution is going to be equal to, so your entire solution is going to be equal to this. Okay, where you know that dn's are just 0 and your Cn's, so we evaluated that these dn's are just 0 and your Cn's is going to be given by this equation. That's it. So that's the entire solutions where your Cn are given by this and your dn's are just going to be equal to 0. Okay, so that's it. Okay, so I believe that is clear, and so maybe I'll stop here for a couple of minutes. So I understand this is the long algebra in this problem, but you can't help. That's how this math is designed. But it's very, I would say, conceptual. Each steps are conceptual here. Like for instance, the orthogonality relations. Decomposing the functions into W1 and W2, writing the boundary conditions, using symmetry. So it's It's little bit involved, I understand, but yeah, so it is, this is how, it is. Hmm. And you know that, okay, so remember, you know that your n will vary from 0, 1, 2 up to infinity. Okay, that's the thing. Okay, all right, so that finishes this problem. Uh, so so maybe I'll come in, so you can have a look, or you can go through how we basically solve this problem. And what we'll do is we'll now solve another different problem, which is a little bit different from the from this problem, which is like, it's a 2D problem as well. So what we'll try to do is we'll try to calculate the flow field that is generated by rotating porous cylinder. I hope you can understand that since this is porous and since the cylinder is rotating, we'll now have, two-dimensional velocity fields. Uh, but we'll use the fact that the cylinder is long enough, and the problem is axisymmetric in nature, meaning that the variables will not be a function of z and theta. So you'll see that the ur and u theta will, these velocities will just be functions of r only, and not depend on the variable z and theta. Based on this, what we need to do is we are required to calculate the velocity field that is u. That's all that we require to calculate in this problem, where it's given that now in addition to the cylinders rotating, there is a radial suction that is taking place. I hope you understand that the suction and the rotation makes the flow feel two dimensional in nature. Okay. All right. So I will pose this problem, and maybe you can think of how to proceed, or at least think of the assumptions that you can use as I have hinted, and then we will see how. So I'll not solve the entire problem. I mean, in fact I'll solve, but I will not show the entire steps. The intermediate steps I will skip, because again this becomes very long to finish it in one go. But I'll just give you a flavor of how the boundary conditions can be, the scheme of non-dimensionalization that we'll use here, and ultimately what the equations will be. Okay. All right, but before that, I'll come in 2 minutes. Till then, you can have a look at, at this problem. Okay, sorry for the interruption. So, okay, so as I was saying, let's try to solve this problem. So I'll give you the physical setup of this problem, as I said. So first of all, I said that the variables are not going to be dependent on z and theta, which means that so not dependent on z is the consequence of the flow of the assumption that the flow is fully developed. Okay, and the independence of theta is because of the fact that the flow is axisymmetric. Okay, so maybe I'll just formally write down the problem statement for you to understand. So you know that the cylinder basically, is long such that you can invoke the fully developed assumptions, and it's rotating with omega in counterclockwise direction. These things you already know. So which means that, so you are also using the fact that, as I said, so you are invoking the assumption that the problem is axisymmetric, and you know and fully developed, I already said. And so maybe I'll also write it down. So axisymmetric and fully developed flow, which means that the variables, which is ur and u theta, these are just going to be functions of the radial coordinate only. And we'll also assume that the flow field is bounded. I mean, it's not an assumption, it's a consequence already. So the flow field is bounded. Okay. Which so what does it mean? So it means that when you move far away from the cylinder, you almost, if you basically consider a fluid chunk of fluid which is situated as far away from at like r very much greater than 1, okay, you will see that the fluid itself is stationary. That's one way of saying it. Okay, so, or maybe you can tell that your ur and u theta, which are just functions of r, they basically go to 0 as r tends to infinity. Okay, that's one way of telling that. Or maybe I should write that the mod of these flow fields. Okay, so what you need to do is, as I said, yeah, so maybe there's one more thing that is given. So we will, so as I said, we'll follow a non-dimensional approach, and it is said that your characteristic radial velocity, which we'll call it as URC, this is equal to the magnitude of the suction velocity U. Okay, and your characteristic velocity in the theta direction, this is given as omega times A, which is the flow field that is generated by the rotating cylinder at r equal to A. Okay, so you see that in this problem we actually have two different velocity scales. This is plausible because of the fact that there are two essentially different physics that drives the flow. One is that there is a suction which is happening on the surface of this cylinder, which is actually causing the fluid to actually penetrate the cylindrical surface. That's one mechanism. And the second mechanism is that you are also rotating the cylinder, and these two mechanisms are kind of independent to one another, right? Because the suction that is created, that is independent of whatever rotation you give. Okay, I mean, to some, it is, you cannot directly tell that it is absolutely independent, but at least you can say that there are two different mechanisms which can generate the flow field. Okay, and since there are two different mechanisms which can actually generate the flow field, I will tell that I also have two different scales for velocity. Okay, because again, the so one way of looking at this statement is that you can still have zero suction and make the fluid move in the theta direction, for which means that you have a characteristic velocity in theta direction, right? And you can still make the fluid, you know not, or you can still make the cylinder stationary and make the fluid, that is to move in to be a function of r along the r direction if you have a radial suction, which is actually kind of penetrating the cylindrical surface. Okay, so that's one way of looking into the fact that why we have a two different scales for velocity in this problem. Okay, and these two different velocity scales are taken to be the suction velocity, the magnitude of the suction velocity, and the magnitude of the rotational velocity of the cylinder, which is the characteristic velocity at in the theta direction basically. Okay, so this is given. So, and they have also said that the scales for pressure is based on the rotation of the cylinder. So this is given as rho u theta c squared, which is equal to rho times omega squared a squared. Okay, That's the scale for pressure that they have given. Remember, pressure scale says I actually asked you guys to derive the scales for pressure. You can see that pressure actually scales as inertia. It can also scale as viscous. If pressure scales as inertia, they basically scale as rho uc squared, which is the characteristic scale for velocity. If pressure scale as viscosity, you will see that pressure actually scale as mu lc by yeah, it's mu uc by lc. That's the scale for pressure. If you compare your pressure scale with the velocity scale, okay. But here they have chosen the inertia scale for pressure, and they have chosen the characteristic velocity as uh, the rotational velocity. I mean, the characteristic theta direction velocity as the characteristic scale for pressure. Okay, in the characteristic scale for pressure, I should say. Okay, the length scale is obvious. So the length scale is just the radius of the cylinder. So these are the scales that they have given to us. So what you need to do is, first of all, write down the boundary conditions. That's one that you need to do. And when I say write down the boundary conditions, I mean that you need to write down both the dimensional and the non-dimensional boundary conditions as well. And non-dimensional. Okay. The second is, once you write down the boundary conditions, you need to derive your governing equation. So derive the governing equations, which I'll call it as G. And after you derive the governing equation, you basically need to solve for the velocity field. For the velocity field, which I said that this is going to be ur and u theta, and also solve for pressure. And also solve for pressure. And you will see that eventually your pressure is going to be a function of r only, and it's given. So remember, it's given that at far field the pressure is equal to some finite value which is given. So P at r tending to infinity is given to be equal to some P naught. That's what it. For instance, you can assume P naught to be atmospheric pressure. That's in your hand. So it's what to say, it's kind of a reference pressure that is given at PR tend to infinity, and the field that you are going to calculate is going to be a field that you calculate related to this pressure at ambient, basically at R tend to infinity, which you can assume to be the ambient pressure, which in reality it would be. Okay. Okay, all right. So then let's get started. So first of all, let's write down the boundary conditions. That's what they have asked us. So so let's do this. So solution. Let's write down the boundary conditions. Okay, so the first boundary condition is that, let's write it for the r direction velocity. So I know that you are at r equal to, okay, I'll write down, as we do, I'll write down the dimensional variables as dash quantities. So you are dash at r dash equal to a for all theta, but we know that this is axisymmetric, so your variables are just going to be functions of r. So I'll not write the theta one here. I know that this is equal to minus u, but I know that my characteristic, that my characteristic velocity in the r direction, this is u, and this is given. Okay, which means I can then write it as urc times ur at r equal to 1, because then this is non-dimensional, and this is equal to minus u, and I know that urc is just equal to u, right? So then this becomes u at ur at r equal to 1 is equal to minus u, which means my non-dimensional boundary condition for ur at r equal to 1, this is going to be equal to minus 1. Okay, that's the first thing. And then let's see this. What is ur? That is my non-dimensional velocity field, r direction velocity field at r tending to infinity. I know that this is 0. Okay, because of the boundedness condition. Okay, that's because of the boundedness condition. Okay, let's see. So this one is the suction at the interface, and this one is your boundedness boundary condition. Okay. All right. So let's then write down the theta boundary conditions. So I know that u theta prime at r prime equal to a is going to be equal to what? So this is going to be equal to omega a. And I can write this as u theta c times u theta evaluated at r equal to 1 is going to be equal to omega A, and I know that my u theta c, that is the characteristic velocity in the theta direction, this is given to be equal to omega A, which means uh, this is omega A times u theta at r equal to 1, and this is equal to omega A, which means this and this will cancel, and then this means that my u theta at r equal to 1, this is going to be equal to 1. Okay. All right. So that's my boundary condition for theta at r equal to 1. And again, the second case for u theta, using the fact that the boundary conditions are bounded, or sorry, the velocity fields are bounded, is that u theta at r tending to infinity is going to be equal to 0. Okay. That's again the boundedness. So this is the no slip, and this is your boundedness again. Okay, that's the boundary condition for what? For velocities. I also need to write the boundary condition for pressure. Then that I know that my pressure when r tend to infinity, this is equal to some p naught. Okay, so maybe I'll call this as p naught. Where remember this p naught now is non-dimensional because I'm writing everything as non-dimensional quantities. So that's the thing. Maybe I should write this as p naught prime and this to be as p naught basically. Okay, so maybe I'll write this as p naught prime, where you know that your p naught, which is the non-dimensional pressure field, sorry, it's the non-dimensional pressure at far field, and numerically this is equal to p naught is basically equal to p naught prime by rho omega squared a squared. Okay, that's how you get this p naught, which for instance, this rho omega squared a squared, this is the characteristic pressure that we have. Okay, that's it. So that's the boundary condition. That's the first task that we are asked to do, and we have, you know, written the boundary conditions here, which are basically these quantities. All right, then we know that once we know the non-dimensional variables, and for writing the governing equations, which we first need to introduce the, sorry, once we know the dimensional variables and the characteristic variables, for writing the non-dimensional equation, we must first introduce the non-dimensional variables. So I will take my non-dimensional ur as ur prime by urc. Okay, I will consider my non-dimensional u theta as u theta prime by u theta c. Okay, and so this, for instance, this is ur prime by u, and this is equal to u theta prime by omega a. Okay, I will write my r as r prime by a. Okay, and I will write my pressure as p by pc, where pc is the characteristic pressure, which is p by rho omega squared a squared. Okay. All right, that's it. So if these are my non-dimensional variable, then you can directly see that. So what you need to do is you now require to write the write down the governing equation. So we know that so we have two velocities, ur and u theta, which means that we now require two equations, which is going to be the r momentum equation and the theta momentum equation. Okay. So the r momentum equation. Okay, so your r momentum equation will give you what? So it is, I'll show you how to do it for the r momentum. I'll assume that you can do the similar exercise for the theta momentum as well. Okay, so it is rho times ur prime del ur prime by del r prime minus rho times u theta prime squared by r prime minus equal to mu 1 by r is prime del r prime of r prime del ur prime by del r prime minus ur prime by r prime squared minus del u prime by del r prime. Okay, so let's invoke the non-dimensional variable. So ur prime, I can write it as urc times ur, where urc I know is equal to u. So then this would be rho. So rho u by, so this is going to be what? Rho u squared by a. See, that's the reason why, because I'll get a uc here and I'll get the uc here. I mean, I should get urc from here I should get an URC from here, and I know that URC is equal to U, which means I get an U squared from here, and I get an A from this R prime basically, because of the fact that R prime is equal to A times R, where R is the non-dimensional counterpart of R prime. Okay, so that's it. So this is rho U squared by A, and then I'll have the non-dimensional quantities like UR del UR by del R, and from here I will have what? Rho omega squared A squared, okay, from this U theta squared, because this can be written as this U theta squared, this can be written as U theta C squared times U theta squared, okay, and this U theta C is omega A, so its square is going to be equal to omega squared A squared, and that's from where you get this rho omega squared A squared, and there is going to be an A here as well, and then this is going to be equal to U theta squared by R, and then we have mu. Okay, so okay, now let's see what we can get from here. So from here we'll get, so okay, from here we'll get URC, okay, by A squared. That's what we'll get, because we'll get an URC from here, we'll get an A from here, and we'll get an A from here. So we'll get mu times URC, but URC I know that this is equal to U, and then this is going to be equal to A squared divided by A squared, and then we'll have this this quantity which is equal to 1 by R del R of R times del U R by del R. So it's just some practice that you need to do in order to convert a dimensional equation into a non-dimensional equation. Okay, minus UR. See, whatever comes from here will have to come from here, because these two terms should have the same magnitude basically, because one term is basically, so these two terms, I hope you understand, should have the same magnitude. That's what you need to realize here. Okay, so this is UR by UR squared minus, from here I should get PC. So PC is equal to rho. So PC is equal to rho omega squared A squared by. So what is PC? Let's see what is PC. PC is rho omega squared A squared. So from here you should get PC by A. So it becomes rho omega squared A squared by A. That's all that you should get. And this is del P by del R. Okay. All right, let's do some simplification. So for instance, I can cancel an A here. I can cancel an A here. Okay. And then what I will do is I'll multiply the entire equation. So I'll multiply the entire equation by the reciprocal of this quantity. Okay. Which is A squared by rho U squared. So if I do that, this coefficients of UR del UR by del R will become 1. This is UR del UR by del R. Okay. Fine. And then I'll have minus rho omega squared A, okay, and then what? And then I'll have rho omega squared A, then this is fine. Then I'll have rho U squared, and I'll also have, okay, hold on, I'll also have an A squared here. Okay, I hope this is correct. So I have this rho omega square A already from here, and I'm multiplying this by A by rho U squared. That's what we'll get here, which means this would just be A cube. That's all. That's the thing that you can say. Okay. All right. I'll just cancel this A squared here. Okay, and then this becomes U theta squared by R, and then this becomes what? So this is mu U by A squared, and I'm multiplying by A by rho U squared. Okay, and then this term is going to be just like this, which is equal to 1 upon R del R of R del UR by del R minus UR by R squared. Okay, and I'm also going to have what? Rho omega square A times A by rho U squared. Okay, and then I'll have del P del R. All right, let's do some simplifications now. So what do we have? We'll have row and row getting cancelled. And is there an A in excess? Okay, I'll have a row and a row cancelled. Okay, this is fine. I think I have written an A in excess, I guess. Okay, let's see. Let's see. This is AQ by this. Okay. Okay, I'm just checking the algebra once. Let's see what do I did. Okay, okay, I think it's fine. It's just all fine up to here. Okay, so this is A, and so this A and A will go. Okay, and this one row and one row will get cancelled from here. Okay, and yeah, so let's write it down and we'll see. We'll figure out. So this is UR del UR by del R minus. Okay, so what I'll do is I will write this as, so this term, I mean this term, I will write as, okay, what shall I do? So I'll write as rho, or okay, rho is cancelled. So this is omega A by U whole squared times A. There is an A, remember, because this is A cube here. So this is omega A by U whole squared times A. And then this is U theta squared by R. And then this is equal to rho A by mu times this function, which is 1 by R del R of R times del UR by del R minus UR by R squared minus this will become omega A by U squared times del P del R. Okay. I think that is what you should get. Let me check the algebra again. Yeah, I think this is fine. Let me check my notes. Yeah, I guess I'm doing this fine. This is fine. Mm. Okay, hold on. So yeah, so I forgot to write this term down. I guess. Okay, so okay, I have divide this. Okay, I'm just checking the algebra once. I think I have missed the A somewhere, so that's what I'm checking. I'm dividing by A times. Oh, okay. So I did a mistake here. So this is A, right? This is not A squared. This is A basically. Okay. So I'm multiplying by the reciprocal of this. So this is not A squared. This is just A, which means this has to be, it has to be A squared. Yeah, that's what I'm thinking. I'm missing. So I'm adding an A extra here. Okay. Yeah. So then this A will not come here, which means this is just this. Yeah, fine enough. Now I think it's clear. Okay. And then I'll have this term, which is fair enough. Yeah, now it's fine. All right. So can you tell me? Okay. Hold on. This is okay. Yeah, no, hold on. And then I have this term. Okay. This term is gone. Okay, let's see this thing. Yeah, I think there should be an U here also, right? So if so please check this term. So it is, so this is, so one U will cancel one U. So I should also have an U here. Okay. I missed this U as well. This is rho UA. Yeah. It is rho UA by mu. Yeah, exactly. See, I cancel one U with U square, which means I should have an U here. I also have a rho and I also have a. Yeah, that's it. Okay, I think now it should be perfect enough. It's a long equation, so it's little bit, difficult to keep track of the algebra. I hope you can see from this. All right. So now can you tell me what is this? So it is what? So it is mu by rho UA. I can write this as 1 by rho UA by mu, and this is nothing but 1 by RE, and this RE is nothing but my suction Reynolds number, right? So this is nothing but my suction Reynolds number, which means I can then rewrite this equation as, so what I can do is I can represent this as 1 by RE. That's all that I can do. Okay. And remember, I also have a quantity which looks something like this. So I also have a quantity which looks something like this, which is omega A by U. So what is this? So this is nothing but your U theta C by URC, right? So this omega A by U actually portrays the ratio of two velocity scale. One is your characteristic velocity in the theta direction and one is your characteristic velocity in the r direction. So this omega A by U signifies, so physically it signifies that how strong is your, how strong is your rotational motion with respect to the radial suction. That's what this quantity omega A by U signifies physically, and we will call this quantity as, let's say, some U tilde. Okay, so as I said, U tilde signifies the strength of rotational motion with respect to the suction. Okay, so it is kind of a non-dimensional number, as you can say, which signifies how strong your rotational motion is with respect to suction. Okay, so then if I write down this the entire non-dimensional equation once again, I will have ur del ur by del r. Okay, the first term is fine. This quantity is just going to give me, this quantity is just going to give me u tilde squared. This is going to give me u tilde squared times u theta squared by r. Okay, and then I'll have what? I'll have 1 by RE, which is my suction Reynolds number, times 1 upon R del R of R del UR by del R, okay, minus UR by R squared. Okay, this is fine. I think this is fine. Yeah, I guess this is okay. And then I'll have, okay, and then I'll have minus, so this rho A, I mean, this omega A by U, this is again going to be U tilde squared. It's again going to be U tilde squared times del P del R. Okay, that's it. That's your non-dimensional. It's involved little bit of algebra, I understand, but this is your non-dimensional R momentum equation. Okay, that's your non-dimensional R momentum equation. Okay, where you can see that you have this U tilde and you know this is a non-dimensional number which is just omega A by U, and you also have your 1 by RE term, which is the suction Reynolds number, and then you have all the non-dimensional variables here. Okay. Yes, I think that's it. I am just rechecking the algebra once, just to make sure that everything is okay. Yeah, I guess it's perfectly fine. Yeah. Okay, that's it. So now the other task is, okay, so now the other task is to find out the non-dimensional theta momentum equation, and you just need to do exactly the same exercise that we do. So I'll not do that. I will leave you, so I'll leave this as a homework to you. Please try this at your end. But I will write down the final form of the non-dimensional theta momentum equation, which is going to be something like this. UR del U theta by del R plus u theta ur by r. This is equal to 1 upon re times 1 by r del r of r times del u theta by del r minus u theta by r squared. Okay, this is going to be your non-dimensional theta momentum equation. So it's exactly the same. You need to do the same exercise as we had been doing for the r momentum equation. You will simply end up getting this form of the theta momentum equation, and where again this re is nothing but your suction Reynolds number that we have just now written. This is your suction Reynolds number, which is equal to nothing but your rho times ua by mu. That's exactly what you'll get. Okay, so that's it. That's your theta momentum equation. But remember, this is not yet. Remember, this is not yet, because we also have an unknown, which is pressure. So remember, this P is also an unknown here, right? So remember, there are three unknown: UR, U theta, and P. So we also need one more equation, which will come from the continuity equation. Okay. So we also need one more equation because we have three unknowns, and that's why we require three equations. So the third one, we'll get it from the continuity equation. And again, the continuity equation, if you write in non-dimensional form, it will just boils down to the fact that del r of RUR equal to 0. Invoking the fact that it's a steady, fully developed, and an axisymmetric problem, you will just have this. Okay. So what you can do is you can integrate this continuity equation. I'll not do, as I said, I'll not do all the steps in this problem. You can integrate this continuity equation and use the boundary condition to find that your UR is just going to be equal to minus of 1 by R. Okay, that's what you should get if you integrate this. So if you integrate this once, apply the boundary condition of the fact that your UR is equal to minus 1 at R equal to 1, and it is 0 basically at R tend to infinity. You will get that your UR is equal to minus 1 by R. In fact, you just need to use here, you just need to use one boundary condition because this is a first order problem here. Okay, so now what you need to do is once you know UR, you require this to substitute. What you need to do is you substitute UR into this U theta equation, and you will see that your U theta equation will simply boil down to an equidimensional equation. Okay, or we call it as the Euler-Cauchy equation. Okay, so if you substitute your UR to be equal to minus of 1 by R in this equation will just boils down to an ODE, which will be an Euler-Cauchy equation. And you know how to solve Euler-Cauchy equation. We had been doing, I mean, at least in some problems, you have actually witnessed how to solve this Euler-Cauchy equation. So try this at your end. So the solution form, I'll give you a hint. You can consider U theta for the Euler-Cauchy equation to be of the form R power k. Okay. So if you take this and solve for U theta, we'll basically get U theta from this equation. And once you get U theta, you need to substitute UR and U theta in the R momentum equation to basically get the pressure. That's it. That's all that you require to do. And then your UR, U theta and pressure is completely known to us. You can show in this problem that you can find analytical solutions. So I'll finally close this by giving you what to say, a heads up that you can find analytical solution to this problem when your Reynolds number is actually less than 1. So given the boundary conditions that we have, you can only find analytical solutions when your Reynolds number is actually less than 1. Okay, argue that what happens. So I'll ask you to do this at your end, given the steps that I have already said to you. Try to argue that why Reynolds number greater than 1 is so actually it's not a real problem, but it's an analytical problem where you will face that you will struggle to find. Actually, it's not possible to find analytical solution given this boundary condition when Reynolds number is greater than 1. So my question is why r equal to so my question is why r greater than 1 is an analytical roadblock, I could say. Okay. Okay, so try to find this out. This is important. Okay, and once you do the steps that I have said, you will actually see that Reynolds number greater than 1 is a problem when we invoke the boundary condition. Okay, so I'll not do this because we had been doing this repeatedly, and I already gave you the hint and I gave you the heads up of how to solve the three variables UR, U theta and pressure. Do this at your end, and if you feel like if you can't, please let me know in the Google I mean in the discussion forum, and I will be happy to address that doubt. But please at least try this at your end and see that indeed you can find analytical solutions to the case when Reynolds number is less than 1. But Reynolds number greater than 1 is actually a problem here. Okay. And try to see why Reynolds number greater than 1 is a problem. And if you have doubts in solving for this, please let me know and I'll help you to, address this. Okay. But I'll not do this here now. And I leave this because of all the discussions that we had, all the practice problems that we solved. I leave this for you to complete the problem basically. Okay. All right. So, okay. So this is where we stop today. Please let me know if you have any doubts. We will, so I'll clarify if there are any doubts in solving, in completing this problem. But I hope the steps and the problem is clear to you. Okay. All right then. Thank you very much for attending or for listening and attending these sessions. We'll meet again in the next discussion hour.